Hi, everybody. I hope everybody is healthy mentally and physically, taking care of yourself and everybody else. And so today our guest is Mr. Stanley Baronett. I don't know
Yes.
how to pronounce that, Baronett. And he is a master's degree student at the University of Nevada in the US. He also has a BA and an MA in philosophy. Is that all right?
That's correct.
That's nice. That's very nice. And a BS in physics. And he currently studying planetesimal formation through stream instability, numerical modeling of planetary disk using magnetohydrodynamics, called Athena++. And stellar evolution in the late stage dynamics of planetary systems. And I contributed to the code Anybody Integrator REBOUNDx, the model model stellar evolution and orbital dynamics. And that's the kind of subject he's going to talk today. So the title of the talk is Stellar Evolution and Tidal Dissipation in REBOUNDx. So thanks for having you here, and the podium is yours. Feel free to share your screen and start the presentation, please.
Okay, great. Thanks for that introduction, Othan, and thanks everyone for inviting me to talk today about some of the work we've done to incorporate stellar evolution and tidal dissipation actually in REBOUNDx. So although we might not always think about it, our sun is actually evolving very slowly, but surely. And in fact, right now we exist here right in the middle, about halfway through what's known as the main sequence phase of our sun. And it's in a pretty stable phase. We have hydrogen burning in the core, and it's in a state of hydrostatic equilibrium. And it's going to stay in this main sequence phase for quite a long time, at least 10 billion years or so for a star our size. But at some point, that hydrogen is going to start to run out, and some interesting things are going to happen in the core. One of them being that a certain amount of helium will accumulate in the center of the core, and the hydrogen burning actually moves to a shell around that. And that fusion process is a little different. And in fact, the helium that's growing in the center increases the core temperature, which increases the burning around in that shell. And this kind of leads to some interesting processes. And in order to maintain equilibrium, the star will actually grow in size. The radius of the sun, for example, will grow as much as 100 times its current radius. And some estimates all the way up to 1 astronomical unit, 1 AU. And along this way, it's going to actually lose a little bit of mass due to stellar winds, and by some models, it can lose as much as half a solar mass, half of its current mass, during these post-main sequence phases. Now, after it leaves the red giant branch, it actually will go through another similar phase known as the asymptotic giant branch, and at this part, the helium that's in the core starts to fuse on its own, creating further nuclear reactions through a triple alpha process. But this nuclear fusion is actually quite unstable. And so you'll get radial growth again as the star tries to maintain equilibrium. And this corresponds to some thermal pulses that we see as these helium burning phases go on and off. And you'll get additional mass loss through the wind during this phase. Eventually, you'll form these planetary nebula as the sun kind of releases a lot of its outer envelopes throughout the solar system. And what we're left over with many, many billion years from now will be a white dwarf, which is essentially just a core left over of the oxygen and carbon from the fusion burning. Now, for the most part, stellar evolution is quite a mature discipline. And because of that, we actually have quite a few state-of-the-art scientific programs that can physically model these stellar life cycles. One of them being MESA, which stands for Modules for Experiments in Stellar Astrophysics. Now, this is an actively developed and strongly supported code. It's actually a 1D stellar evolution code. And some of its features include that it's open source, it's also modular, and it's quite fast. It supports parallelization, features, so you can run this code on high-performance supercomputing clusters and utilize as many cores as possible to assist in the integrations that it's doing. Some of its advantages of using MESA over some other stellar evolution codes is that it has comprehensive microphysics and actually supports detailed chemistry. So there's actually quite a lot of equations of state packaged in with it. And in fact, it supports variations of wind schemes, which control the mass loss during these red giant branch and asymptotic giant branch phases. So what we can see here on the right is actually a 1 solar mass test that is available out of the box with MESA. And what we're showing right here specifically is just a slice of the post-main sequence to the white dwarf evolution. And so in the top plot, we have the sun's mass as a function of time in units of solar masses. And you could see as it leaves the main sequence, it begins to lose some mass, and it actually enters this rapid mass loss right before what's known as the tip of the red giant branch, being when the sun's radius increases very, very strongly up to a point. And it loses as much as 2/5 of its mass by the red giant branch phase, end of the red giant branch phase. Afterwards, when it enters the asymptotic giant branch phase, the mass loss is a little bit slower and more constant. Although those thermal pulses I mentioned earlier crop up, you could see here the sun's radius has like a little thermal pulse right there, and that actually corresponds to some drops in the mass as well. And by the end of the asymptotic giant branch phase, the star has effectively lost half of its mass, as we discussed before. And just for reference, if we look at the bottom plot here, being the sun's radius, that 1 astronomical unit is about 215 stellar radii. So we haven't quite reached that yet. But what does this mean for our solar system, right? We got all these dynamics potentially going to happen as the sun drastically changes later on in its life. And so much of the literature agrees that Mercury and Venus are most likely going to be doomed. But what about Earth? Well, aside the fact that this is going to be billions of years from now, it's curious to think about what might happen to the Earth. And in fact, there's not a complete disagreement in the literature on that. In fact, just a couple examples here. Some authors argue that the Earth will survive by the end of the red giant branch and asymptotic giant branch phases. Other authors argue the Earth will become engulfed by the tip of the red giant branch, for example. In fact, one author you could see here changed his mind between these two papers. And so where's the source of this uncertainty? Well, part of it has to deal with the fact that we don't have an exact expectation of how the mass will be lost, how those mass loss rates will occur. And that mass loss rate will directly affect the adiabatic expansion of the orbiting planets. And so it may or may not allow the orbiting planets to escape this growing envelope of the sun, depending on how quickly it loses mass. Another interesting aspect to consider is if a planet gets close enough to the sun during these phases, you have to consider dissipative tidal interactions that can occur that may also affect whether or not a planet can survive. And so to look into this, what are some of the tools that we can use to investigate these post-main sequence orbital dynamics? And so we looked into REBOUND, which is a modern flexible n-body integrating code. And it's written in C. It has a core C, but it is wrapped conveniently in Python. So it's very easy to use, especially if you're just starting to program. You don't have to know any C programming or anything like that. And it was designed, part of the reason for using C as its core language is that it was designed with memory and computational efficiency. And so it's quite effective. It's also open source, and it supports parallelization as well, if in case you want to do very long extended integrations or asteroid simulations with thousands and thousands of particles, you can parallelize this to get much better efficiency. And another unique thing is it's actually bitwise reproducible. What that means is it has a simulation archive built in where you can stop and save the simulation you're running and resume it either on the same machine or on a separate machine, and you'll get the same results every time. So which is very good for reproducibility. Another feature is that it comes with a lot of different integrators out of the box. By default, it has a very high accuracy 15th order integration with adapted time steps scheme. It also includes a very fast Wisdom-Holman scheme. It has a hybrid scheme named Mercurius, which is in reference to the existing well-known Mercury code. And it in fact has a time reversible integrator that they call Janus, which allows you to both integrate forwards and backwards in time to get the same results, which is quite interesting, depending on what kind of investigations you're looking into. Now, we have this MESA data that we just showed in a plot earlier, and if we want to use this in Rebound, there's a couple ways we can go about doing this. Early versions, we were just manually adjusting the mass in the Python code. Although it's convenient, it's very slow. The performance is not very good. And so in order to make this generalizable and also usable for the community, we wanted to introduce new code to accomplish integrating MESA data or any other kind of parameter data in real time, more or less, with the Rebound integration. And lucky for us, already existed a REBOUNDx, which is the official extended library to Rebound, and it's REBOUNDx standing for extras. And some of the additional physics that it contains that you simply just load in the program are things like post-Newtonian correction, like for general relativity. It also supports radiation forces, for example, Poynting-Robertson drag. We're actually currently developing an additional module to model the Yarkovsky effect. And all in all, it's a very flexible and modular framework that allows you to add additional physics, especially non-conservative physics. And so this was perfect for what we wanted to look into doing. So how do we accomplish what we're trying to achieve here? And what it is we want to leverage a numerical scheme that can couple these different integrators that are dealing with different physics in a modular way. And one simple, powerful class of numerical scheme that can do this are splitting schemes. And in our case, what this is going to do is it alternates between evolving an orbital step in the Rebound code or n-body code, and in the stellar evolution step, using these fixed time steps from the splitting scheme. So by doing it this way, by calling the integrators separately, we actually minimize code duplication. So in other words, we don't have to write stellar evolution code for Rebound. We can utilize what's already there, what's state-of-the-art, what's fully supported, and basically combine the abilities of the two. And so suppose we have a discrete numerical solutions for the parameter evolution and then also the n-body evolutions in isolation. If we have that, then theoretically with this we can construct a first-order splitting scheme that ideally would alternate between an n-body step. You can see here these markings here show the DT and body steps that occur, and alternate between that and then a parameter step. You can see here, this is the parameter evolution 1 integration step in MESA. And that ideally these steps should land identically. So in other words, in one, you integrate one code for one splitting interval, DT split here, and that's going to be made up of many n-body steps. And then you'll also evolve the parameter evolution for the same step. Now, in the extreme limit where the splitting time step gets very, very small, this actually approximates the true solution, and it actually helps us appropriately choose a size for the splitting time step that's much less than the time scale of the parameter evolution. But precisely adhering to this would actually force us to have the parameter step and the n-body steps land exactly at the same time every time, which can be quite inefficient if you're trying to do several n-body integrations, let's say for the same stellar model. So you can imagine you don't want to have to rerun the MESA simulation every time you want to do the simulation. It's better to just have one stellar evolution model, and then you can run as many Rebound simulations as you want using that. And so the way we get around if the steps don't line exactly is we can actually interpolate the value. So you could see here that MESA in fact uses an adaptive time step, which makes it even almost impossible to even hope to get the time step to match up with rebound. And so if you have these points, for example, let's say this is the star's mass, this is some discrete solution that MESA produces, we can use an interpolation scheme to figure out what the value would be in between these two discrete points, and use that to update the information that's in rebound. One of the ways you can justify doing this is because the error from the interpolation scheme is actually very negligible compared to the error of the splitting scheme itself. And in our case, this lets us use a much more efficient approach of running a single model, like I said, and interpolating results for a number of different n-body integrations. And so we implemented this in Rebound, and it's entitled the Parameter Interpolation is the name of the feature. And again, it allows you to load any data. In fact, it doesn't have to be stellar evolution data. It can be any parameter. So if you want to model atmosphere on a particular planet as this n-body integration's occurring, you can do that as well. In our case, we are loading MESA history outputs, as we saw earlier from that plot. And all it takes is just two simple arrays per parameter that you want to evolve. So one being the monotonic time series of the values, and then the values themselves for whatever parameter is evolving. And again, it uses interpolation to decide or to figure out what the value of these parameters would be in between the actual data that you have based on wherever rebound's at. And we're currently, the default interpolation scheme is a cubic spline, although we have written the code to support additional schemes in the future, should there be any desire for that. And by putting this code into the C core, it's immediately 3 times faster than Python. And not only that, but it's machine independent. So what that means is you don't have to use any other additional libraries to get this to work in your code. You just simply load rebound and it's available. You don't even need to load the feature itself. It's always available. And it also features an optimized interpolation search function. And what I mean by that is, as rebound is going along, it's either forward or backward integration. It's very efficient in how it knows where to go and interpolate next. And this search algorithm is actually log 2n faster than just a simple binary search. So it's very efficient code. And it also supports forward and backwards integration. So if you do happen to use this Janus integrator, you can do a backwards integration and it'll interpolate the data just fine. And even it supports arbitrary spline calls so if you just want to query your parameter data using rebound, you can just ask it, give me what the value of this parameter would be at this particular time, and it'll interpolate that for you. But we do want to note that as a word of caution, that it is going to be timescale dependent, as I just mentioned a little bit before in the previous slide. That so if you have a parameter that's changing very significantly on some dynamical timescale, so for example, you have some mass transfer that occurs at the pericenter, let's say, of a very eccentric orbit. If you have something that very extreme like that, then you're going to need to require a specialized numerical scheme to accomplish that, to model that accurately. But again, in our situation and for many astrophysical scenarios, when the parameters themselves change very slowly compared to the dynamical timescales, like what we're going to be viewing here in a minute, as long as these changes are adiabatic, then you can modify these parameters in rebound between the time steps without really losing any accuracy. So you can see the result here. This is using the data that we just saw earlier. Specifically, it's a 4 million year simulation just before the tip of the red giant branch. You can see here in the bottom plot of these distances, the red line being the sun's radius. This blue and yellow line is the Earth's orbit. And so what we did was we initialized the Earth at 1 AU. In reality, by the way, the Earth would have already expanded somewhat outward, because as you can see here, the mass, sun's already lost some mass by this point in the RGB phase. But regardless, if you started out at 1 AU, there's this mass loss, and correspondingly, the Earth will adiabatically expand outward. And we see that it reaches as much as 1.5 AU by the tip of the red giant branch. And as you can see here, the sun's radius reaches out to about 0.8 AU. And for reference, Venus's perihelion is around 0.72 AU. And we actually did this twice using 2 different splitting scheme intervals on the order of 400 years. Every 400 years, update the parameters, or every 4,000 years, update the parameters. You can see the two are indistinguishable, and they've actually converged to the same solution for this particular problem. So let's now move on to the second source of uncertainty we discussed earlier, which is how the future of our solar system would look, and the terrestrial planets in particular, when you have these close encounter tidal interactions. So some of the motivation for us to looking into this is that in Schroeder and Smith's paper in 2008, they state that the sun will virtually stop rotating after the main sequence. And this is due in part to conservation of angular momentum, but also magnetic braking that actually results from interactions between the star's magnetic field and stellar wind. Furthermore, for a highly evolved red giant branch sun, tidal friction in the outer convective envelopes of the star will actually retard any tidal bulges that form on the solar photosphere. You can see that here in this right side diagram. This gives you a physical picture of what's going on. So you have this closely orbiting body, let's say the Earth, for example, and the Earth will raise a tidal bulge on the star, but because the star's rotation is almost zero, and because of the convection lag that we just discussed, these tidal bulges actually lag behind the position of the Earth. And because of this difference between the two, this creates a non-conservative drag on the planet, and in this particular case will steal orbital angular momentum from the Earth, and slowly the Earth will its orbit will decay and it will begin to migrate in toward the sun. So it'll actually contribute to the nearby object becoming engulfed by the sun. And so one way to model this is using Hutt's weak friction tidal model that he developed for stellar binaries, described here by this force prescription, where the first term is just the Newtonian attraction between the 2 point masses, and then all the other terms are the tidal effect from the perturbing acceleration from the nearby body. Q in this case is the mass ratio, simply just of the nearby body over the central body. K2 is this perturbed body being the sun, its second degree potential love number, describing on the surface of that body. And then more importantly, there's this tau factor here, which is this small constant time lag that corresponds to the slight change in both the amplitude and the direction, or the misalignment, so to speak, of the tides that you see here, this misalignment. And so in implementing this in a rebound, we wanted to keep things very simple as a first step. And so we didn't model the stellar or the planetary spins at all. But when it's activated, it actually applies to all the other bodies in the simulation. And so, in other words, tides can be raised on either primary or the orbiting bodies, or both. And I'll explain that here with this diagram. So you have your primary first body in the simulation, and we give it some mass, a physical radius. It's going to have some intrinsic spin, angular velocity omega. It'll have its tidal love number, and it may or may not have a small constant time like tau. Once you set these, then the other bodies in the simulation will do the following. So for example, if you have this first mass where it has some non-zero mass and a physical radius, it will actually raise a tidal bulge from itself onto that sun. The second mass, for example, we've given it some non-zero mass, a physical radius, and its own potential love number. And by doing that, it itself will produce tidal bulges on it due to the star. But again, as we discussed, it'll generate a tide on the surface of the star itself. And then finally, if we have this third mass where it's, let's say, a test particle and its mass is zero, it won't produce any tides of its own on the star. However, it will feel the tidal force effects produced by all the other, the superposition of all the other tides produced by all the particles in the system. And so specifically what's important, whether or not you end up with the equilibrium case or some dissipative case, depends on whether there's this constant time lag tau set. So by default, it's zero, which means you'd get the instantaneous equilibrium case, where it basically just provides a conservative radial non-Keplerian potential. So the total energy will be conserved, but the pericenter of the nearby bodies will precess. But when you have a non-zero tau, this introduces dissipation in the system. And so this delayed response causes eccentricity dampening, and it'll actually migrate the bodies inward or outwards, as we discussed, depending on whether or not they orbit faster or slower than the spin of that tidally deformed body set by that omega case here. So now, because of this very simple first step model that we did, there are some limitations, of course. One is that the effect does not evolve the spins. So in other words, it's only applicable to cases where the orbital angular momentum change due to the tides has a negligible effect on the spins, or whether or not, or in cases where the orbital angular momentum of a nearby body is much, not orbital angular momentum, orbital angular velocity is much, much smaller than the spin angular velocity of the central body. So in other words, you must consider carefully whether or not there's more angular momentum needs to be exchanged between the system than is available in the spins. Furthermore, the quote unquote spins are fixed. The spin angular momentum vectors are fixed and aligned with the reference z-axis of the simulation. So if a body's orbit is inclined with respect to the xy plane, for example, then its spin will actually be inclined with respect to its orbital plane. And then finally, there's actually, for efficiency purposes, there's no direct tides between the perturbers. So as you can see again in the diagram, you'll have the force effect between the primary and any of the secondary bodies, but there won't be tides raised between each body or the force felt from that. So here we have this tide constant time lag, TCTL as we call it. This is a unit test showing how it fares against a theoretical prediction. And so we just set up a very simple case, again, near the tip of the red giant branch. In this case, all the star's parameters are fixed. So we have already some little bit of mass loss, and also the sun's extended out already to about 0.85 AU. And we just observe how the Earth's semi-major axis decays as a function of time due to this force, this dissipative force. And you can see the blue dot, which is our simulation results, map on very nicely onto the theoretical prediction that we calculated analytically. And similarly, if we add a little bit of eccentricity to the Earth that's nearby, we'll notice that during the same, in a separate simulation, but during the same time frame, that eccentricity is dampened over time as we expected from that physical model. So now to further showcase the capabilities of these new features in REBOUNDx, we actually want to demonstrate some instances where we include both the dynamical stellar evolution and the effects of dissipative tidal interactions, both running simultaneously. And so in this very dense graph here, what we see is a series of single planet simulations where we've started out planets at even increments away from the star. So again, this is just before the tip of the red giant branch. This is being around 5 million years or so. And we start a planet out at about 0.4 AU, 0.6, increments of 0.2, all the way out to 1.4 AU. And we also observe the effects of both with the tides turned off, just the purely adiabatic expansion case, and then also with tides turned on, and how the effect of the mass of that planet, how it induces a stronger tidal interaction. So as you can see here in this lower panel, in the lower case, this blue line here, whether tides are turned on or off, it's going to be engulfed. So in other words, its adiabatic expansion cannot outrun the growth of the sun's radius. Same thing that almost happens for this orange line here, although it just barely makes it out at the end there. But you'll notice that once the tides are turned on, in the case of this orange line, that it will, because of the dissipative tidal interaction, it will become engulfed. And in fact, that force felt stronger when the mass is increased. And you could see even all the way out for the furthest planet out at 1.4 AU, that if that planet has about 100 Earth masses, it too will not survive that tip of the red giant branch phase, and will in fact get captured and engulfed into the star. So because we have both, because we were discussing earlier the splitting scheme and the efficacy of it, we wanted to look into the effect of how that splitting scheme interval, or that DT split, affects the dynamical results, right? Theoretically, we discussed that the smaller the interval, you should get more accurate solutions. You should approach a true solution. And so as you can see here in these two plots, these trend lines, and I'll discuss real briefly in the top plot, what we're observing here is the engulfment time of a one Earth mass planet at about 0.7 AU from the sun. And so as you can see that as you shorten the splitting time interval, this is the relative error with respect to the difference in the engulfment time of that planet with respect to the most accurate time. So the most accurate interval we use here is 1/10 of a year. And so everything you see here is a relative error with respect to that. And so as you can see, as you make that splitting interval smaller, the difference with that most accurate result decreases and begins to converge to some point. But more importantly, what you notice is that of course, as you make this splitting time interval smaller, it will increase the overhead of the code, right? Because it's having to compute and interpolate these values more frequently. And so this adds, you get this diminishing returns effect. So at some point, you will get more accurate answers, but the amount you gain in accuracy is outweighed by how much more runtime it adds to the simulation. Same thing with the bottom plot. Here we're looking at the relative error between the final semi-major axis of a one Jupiter mass planet at 5 AU during this expansion case where you have the stellar mass loss. And as you can see, again, you're getting accuracy as you go down into smaller and smaller increments, but similarly, the runtime will increase. And in fact, it's a lot worse in this case, getting as much as 10 times or more runtime with the smallest intervals. We also wanted to look at the time performance with this code because we want to make sure that the code is in fact efficient and it's not going to cause any burden in introducing it if you already are using Rebound or if you want to incorporate it in future simulations. And so what we did in these cases are run 4 different setups. One where we have the fiducial case, there's no effects loaded whatsoever. Where the second case we have just the parameter interpolation, so no tides. The third case, tides only, but no parameter interpolation. And then the last one being both of the effects simultaneously. And as you can see, after several runs calculating the average and standard deviation, there's only a minor increase in just using the parameter interpolation by itself, less than 2%, which is virtually nothing. And then using the tidal interaction or both of them together, it gets to be about 15% increase or so. But again, we believe it to be very manageable overall at scale, especially when you're talking about very, very long integrations on the orders of hundreds of millions of years or maybe even billions of years. This is going to be a very small fraction of that total time it takes to run those simulations. And so now at this point, I'd like to show how easy it is to use this new code and how to set it up. And so what I'm going to do is I'm going to show a demonstration here where we're going to be doing this on Google Colab. I'm not sure if some of you are familiar with this, but what I'm going to do is I'm going to post this link in the chat here, and you're welcome to follow along. So I'll post this in the chat here and give everyone a couple seconds to connect if you want. Otherwise, all you have to do is just follow along what I'm doing on the screen. But again, feel free to interact as well. So I just posted the link in the chat. If you want to load that up on your own machine, please do. And I'll kind of go through this really quickly. It won't take very long on how to use this code. And so just briefly, for anyone who's never used Colab before, if you're familiar with Jupyter notebooks or the Jupyter project, Python notebooks, this is effectively that just running on Google servers. And the nice thing about it is we don't have to worry about it just runs in using their servers out of the browser, so there's no setup. You can just get right to running the code. And so what I'm going to show here is just 2 simple examples of stellar evolution and the tidal effect that we've incorporated into Rebound. And again, feel free to follow along. Otherwise, you could just follow along with what I'm doing here. So in this first case, all we're going to do is we're going to set up a very simple Sun-Earth system here. And so if we look at the code really briefly, we import Rebound, and we define a function where we'll create our simulation. And it's just a couple of lines. The first line, you create the simulation object, calling it using Rebound. The next line, we simply set the units that we want, which is very convenient. You don't have to do any kind of numerical code unit calculation. You simply tell it, I want to use years. The distance will be in AU, and mass will be in solar masses. Then we add our particles. So we add the first particle being our sun with a mass of 1 solar mass. And then we'll add an Earth at 1 AU. But for this particular example, we won't add any mass to it because we're just going to be looking at how the stellar evolution affects its expansion. And then we can set an integrator here, which in this case we set the integrator to be WH fast, which is pretty accurate for what we need to do, and it's going to run very quickly. So to execute the cell, all you do is you simply click this play button here, or if you're familiar with Jupyter notebooks, you can hit Control or Command Enter if you have the cell selected. So I'll just go ahead and click this play button. You'll notice you might get this this warning. This is just to let you know that this notebook that we're interacting with is actually being hosted on GitHub. So Google's just saying, just be aware, make sure that there's nothing malicious in the code, which I can assure you there isn't. And so once you're comfortable, go ahead and hit run anyway. And oh, by the way, I'm sure some of you encountered this already. You might have had to log into your Google account up to this point, but assuming you made it, here we are. And so we're running that, so it'll install Rebound in the background. And so while it does that, we can go on to this next cell, which is the meat of it, which is what we're going to integrate this system that we just set up for 10,000 years. And we're going to verify that the Earth's semi-major axis doesn't change. So in other words, we're not going to be using the parameter interpolation just yet. We just want to make sure in a fiducial case that you run it for 10,000 years, nothing's going to happen, right? And so this first block here, this is just some basic setting up of arrays to store some of the output. We're going to store 1,000 outputs and over the course of this 10,000 years. So this corresponds to a splitting time scheme when we do get to that point of interpolating of about 1,000 years, sorry, 100 years. And then we're going to store the Earth's semi-major axis over this time. And so this is the key part right here, is this for loop. And it's very simple to set up and execute and Rebound. So we're going to loop over this series of times from 0 to 10,000 with even spaces. And at each time that shows up, we're going to tell Rebound to integrate to that time, which in the background, this is going to be made up of several time steps, smaller time steps. But we're only going to interrupt the integration at these 1,000 outputs, so to speak. And when that occurs, we're going to store the Earth's current semi-major axis at that point. So we're going to get 1,000 data points for how the Earth's semi-major axis changes, or in our case, we'll see it doesn't change over that 10,000 year period. And then finally, we just can plot this data once we have it. So we can click play here, and it'll run the code, and only takes a couple seconds here, and we'll see a plot show up at the bottom, and we can see right there, only took about less than 5 seconds. And unsurprisingly, nothing much happens. The Earth's semi-major axis stays at 1 AU for the entirety of 10,000 years. So now we want to show what happens when we use this new code. So what we have to do first is define these arrays that are going to that will interpolate how the sun's mass is going to evolve. So you can either import an external data file if you have it already, either from MESA, or if you do your own integrations or simulations and you have data from that, you can import that externally. In our case, we're just going to simply create 2 simple arrays here. So what we have specifically in this case is just an exponential mass loss rate. So in other words, there's an e-folding time scale of about 10 to the 4 years, 10,000 years. So at the end of 10,000 years, the sun has lost all its mass down to 1 over E, and that's its final value. So it's just 5 different points that we're going to be interpolating across. And then this next line is we're going to introduce REBOUNDx. So we load REBOUNDx and attach to the simulation. And then again, there's no loading explicitly required for this interpolation. All you have to do is create what we call an interpolation object. And these, you'll have one of these objects for every parameter that you want to interpolate. So hypothetically, if you want to also track the sun's radius, as we did in some of those plots that we showed, that will have its own object. Same thing with the luminosity, et cetera, et cetera. And so you create this object, star mass, and you pass the two arrays that we just created, being the times associated with the mass loss, and you tell it what interpolation scheme you want to use, in this case, the cubic spline we discussed. And then for good measure, we're just going to plot that data so we can see what it looks like. So I hit play here. It's going to install REBOUNDx real quick, and then it's going to attach everything that we wanted, and it's going to produce this plot that we can see we have 5 discrete data points throughout here. And this is the data that we're going to now interpolate across in our simulation. And so to do that, all we need to do now is just go back up to the cell, and there is this line that I had commented out here. And all we're going to do is we're going to uncomment that line. And what that line does is it just updates the mass of the star by interpolating that stellar mass with that object that we talked about at that time. So in other words, whatever time it is in rebound, find out what the mass is at that point, update the star. And so we'll go ahead and run the code again now that it's uncommented, a couple seconds again, and then we should see in a moment, and there you go. And so you could see that the Earth, as we expected, adiabatically expands outward in concert with this mass loss out to about the factor of E by the end of this 10,000 year simulation. And you can see it was very easy, just a couple lines of code to implement. So if you're familiar with Rebound, it's really no time at all to start using this just by loading in REBOUNDx. And so next we want to just show briefly the tidal effect that we've added. And so we're going to do a similar thing here. I'll go ahead and hit play for now. On this cell, what we're going to do is we're going to create a Sun-Earth system, but this time we're going to assume that the sun's lost a little mass. So in this case, it's now at 0.86 solar masses. And so what we're doing is we're trying to recreate the situation right before the tip of the red giant branch. And in this case, we're actually going to give the Earth some mass. We're going to give it its proper mass in terms of solar masses. We're going to put it again out to 1 AU, and we're going to give it a slight eccentricity of a 0.03 in this case. Again, called the integrator. Because the Earth has some mass this time, and we have a 2-body system, we actually want to move the coordinate system. We're going to center it in on the center of mass. And so next, we immediately load REBOUNDx because we want to use this force. And this is where you have to explicitly load the force, tides, constant time lag, and then we attach the force to the simulation here. And then that's it. That's how we defined our simulation setup, and we've already run that cell. So now we can move on to the specific configuration options you have to use for the tides to work. So in our case, what we need to do is we need to add a physical radius to the sun, as we discussed earlier. And so here we give it about, and again, this is in AU, we give it a radius of about 0.85. And then we also assign it that tidal love number that we discussed. And in this case, it's going to be 0.03. And so once this is set, tidal bulges will raise on the star. But because we haven't set a constant time lag tau, this will be the instantaneous equilibrium case. So again, we're going to get conservation of momentum, but we will observe the pericenter of the Earth precessing over time. So to observe that, what we can do is we can actually run this simulation for 5,000 years. And what we'll do is, as we go along, we're going to store the longitude of the pericenter for the Earth as this simulation goes through, and then we're going to plot it really quick. So I'll go ahead and run this. I'll run this code cell. Oop, that's not what I was expecting. Give me 1 second here. Let me rerun this. I might need to rerun the first one here. Let's rerun that cell. I'm going to rerun this cell again as well, and then I'm going to rerun this cell, and hopefully it shows me what I'm expecting. There we go. Okay. So as you can see here, the argument of the longitude of the pericenter is precessing slowly as time's going on, which is what we expected. But now we want to look at the dissipative case. So in order to do that, we have to give the star some constant time lag. In our case, it's going to correspond to that that delay on the photosphere, and then we also need to give it a intrinsic spin. By default, omega is assumed to be 0, but we are explicitly making it the case. But again, you can leave this line out, and it'll work either way. And so again, we assign it a love number and then a small constant time lag. So we'll go ahead and run the cell. That's going to reset the simulation, add the new configurations and the parameters to the star. And so now we're going to reintegrate this system, this time for 25,000 years, and we're going to observe the Earth's semi-major axis over time. So we'll go ahead and run the cell. So this is a very similar cell to the one we saw earlier, where we're storing the semi-major axis of the Earth and its eccentricity over time. And it's going to just take a little bit longer to run because we are running it for about 5 times as long. And as you can see here, the Earth's semi-major axis decays. And so this is that migration that we discussed due to the orbital drag. And similarly, we can also plot how its eccentricity changed over time. And as you can see here, the eccentricity of the Earth began dampening because of the dissipative tidal effect due to that force. And so that's it. It's very simple. There's just only a handful of lines you need to add. So it's really no burden at all to use this new code. And so finishing up here, I just want to mention a couple potential applications to just get your taste buds flowing about maybe what you can do with this code. So of course you could do full end body integrations of all the planets simultaneously. You can even include hundreds of thousands of asteroids. You could observe what can be happening there. So you can look at, for example, instability timescales of these systems. You can look at white dwarf pollution for asteroid drift, especially how the dissipative tidal drag affects that as they get closer and closer. You can even look at hot Jupiters. Those are very close encounter type situations, and you can see how usually these hot Jupiters are associated with post-mean sequence stars. So you can use both features to observe what would happen there. And then finally, you can do exoplanet resonance breaking. And one of the ways you can do that is you can model these exoplanet stars, the host stars for these exoplanets in MESA, produce the data, and then use that data in a rebound simulation where you've set up the system, the exoplanet system, based on our observational data, and then see what happens there. And of course, we absolutely encourage any contributions to the REBOUNDx project. It is community driven, and we're hoping that by having people add to the library with additional physical effects, especially in the research that they're doing, that it will become a very comprehensive package that everyone can use. So thank you for your time. There's a couple links here if anyone's interested. And of course, you could save that Google Colab notebook link at any time and play around with it. And at this time, I'll take any questions. Thank you.
Thanks, Stanley. Fantastic lecture. It was not a seminar, it was a lecture. Very, very, very good, very clear.
Thank you.
I think it was great. So now we are open for questions. Anybody would like to make a question or comment, please?
Stanley, can you hear me?
Yes, I can hear you, Ricardo.
Yeah. Okay. So I have a question. Did you compare your implementation with some other codes that evolve the spin of the central body? To see
No.
how
Yeah, not. Yeah, I do know that, for example, Dimitri Veras has a, he's done a lot of tidal cases using Mercury, and I think the Mercury T version of that code. So when we get to that point, if we do start to look into modeling the spins, we will absolutely look at the existing literature on that, and then most likely we'll want to compare our results for that with that. But at this point in time, it's just a very simple model, as we explained, and so we haven't looked into the results against the spin. So we're not. Maybe you have some knowledge about whether or not, even with this simple model, how well it captures some of those spin situations where it is modeled. But at this time, I don't have any numbers for that or comparisons.
Well, I ran some simulations trying to compare those two, and well, so far so good. I mean, the evolution of the spin doesn't change much the results.
Okay.
I tried to implement pseudo synchronization, like it's kind of evolving the spin, but not like quite evolving. And only for like very extreme cases, you have some differences.
What are some of those extreme cases? Can you give an example?
Yeah, sure. For example, if you try a sun-like star and a planet like Jupiter, like super close to the star, like with some major axis of 0.5, 0.7 AU, then you start to see some differences. But other than that, it's quite similar the results.
Yes. Okay, good. Yeah, good to know. Yeah, I think for example, like in this plot, when you're having this radial expansion of the star, for the very close bodies that are going to be captured, especially if what you're looking at is just whether or not a particular planet will become engulfed, it's probably safe to say that modeling the spins doesn't really change the results too much. But I could see exactly what you're saying. Like in the case of like a very close by nearby hot Jupiter, if you want to get the dynamics just right, yeah, you're going to need to model the spins for sure. No question.
Yep. Thank you for the lectures. It was very nice.
Thank you.
Thanks, Ricardo. Anybody else? Any more comments or suggestions or questions? Oh, there is one in the chat.
In the chat, yeah. Oh, yeah, I see. Okay, how are planetary collisions treated in this program? Oh, good question. So, believe it or not, REBOUND actually has I don't have a slide on this, but REBOUND has out of the box collision detection, and that was before we even added our code or anything like that. And there's actually quite a few options for the collision detection. One of them being you can set a threshold around the particles in your simulation. So, for example, let's say you want to set the sphere around these particles to be like, let's say, the Hill radius or the Hill sphere, and you can configure the code so that when a close encounter happens, in other words, when two particles in their Hill spheres get close enough, and it'll actually switch the integrator to a more accurate one. So that this is actually what this Mercurius hybrid integrator does. And so what it does is when the particles are nice and far away, it will use a very fast Wisdom-Holman scheme. But as soon as you get a close encounter where the particles may come by very close by, it'll switch over to this very high accurate 15th order scheme to get the close encounter, more accurately to capture it. And then there's a slew of options you can use to how to handle the collisions out of the box. So, for example, you can set it up where if there is a collision, the two particles can merge. So it effectively removes one particle from the system, adds the mass to the main one. You can have you can just zero out the secondary particle without adding it to the mass. So it's very flexible, very a lot of options to handle collisions. And so for our particular simulations, especially the ones you see, let me come up to this. For example, in these simulations, we just did a very simple collision detection where as soon as the physical radius intercepts the physical radius of the star, we add the mass of the orbiting body to the central star and remove it from the system. And so that's all we've done in this situation. But there's lots of options you can use to handle the collisions. So hopefully that answers your question.
Okay, good. Ricardo made a comment here. You can even stop the simulation if a collision is detected. So
exactly. Thank you, Ricardo. Yeah.
Okay, good. Anybody else? Any more comment or question? So I think that's it. So I'd like to thank you again. It was great. I think some of us are going to watch the video again. And I think it's a very interesting project. And this idea of being open source is great, and collaborative work, I think it's the new wave of doing research. So
yes,
congratulate you and everybody involved in this kind of project. Thank you very much.
Thank you. Thanks again for inviting me.
Okay. And just before we finish our meeting, I think we can stop the recording. We have here